ounces of stuff in it. That I could run the same kind of problem string, and I'm not going to do them all, but can I get to 100 bottles? How many ounces are in 100 bottles? Hey, just add 2 zeros. Does that work? No, so we really have to talk about place value shifts. But does everybody agree that would that be 320 ounces? Is that right? Could I then ask you for 99 bottles? And could you do the same kind of thinking and reasoning to find 99 times 3.2? What is 320 minus 3.2? Well, we can think and reason about that. What's 320 minus 3? Is that 317? Now I got to get rid of 20 cents. That's a 2. 20 cents. What's $317 minus 20 cents? Is that 316.80? And what problem did we just do? 99 times 3.2, thinking and reasoning. Yeah? Multiplying decimals, which is a new 5th grade standard. This is how we should be multiplying decimals in our new 5th grade standard. Thinking and reasoning about multiplying decimals. Could I do the same sort of similar thing where I can ask you for, hold on, I gotta find my number, for 313.6 ounces, how many bottles? 313.6 ounces, how many bottles? What's the difference? Is it just 1 bottle from the 99? Or is it 2 bottles from the 100? Either way. Or now, you might say, Pam, use the same numbers, same relationships. Yeah, because they're the hardest ones. I just gave you the hardest division for like 3.2, because look, 313.6 divided by 3.2, have fun.
No, thank you.
Or think and reason the way that we just did. And we're solving long division with decimals by thinking and reasoning. Now the cool part is, we just did multiplication and division, thinking and reasoning with whole numbers and decimals, but we also built proportional reasoning at the same time. Because every one of these ratio tables, and that's what this model is called, every one of these ratio tables, that's a set of equivalent ratios. Those are all equivalent ratios. Through that whole, that's what a ratio table is. So we're building proportional reasoning. Now, caveat, the 2 problems that we just did, we're building proportional reasoning using unit ratios, yeah? So we better get to non-unit ratios. But before we do that, I just want to say, if I'm a high school teacher, an 8th grade teacher, even a 7th grade teacher, and I'm doing that, then I would want to take those numbers back, use some technology. I would throw, this is a TI Inspire app, you can use one of your favorite graphic calculator, throw those numbers into a list. So can you see how, this is kind of small, but can you see how I have 17, 8-pack has 17 sticks? I'm not going to do slides, so it'll take a little bit too long, but have kids put that into a list. Then once it's in the list, then can I look at the scatter plot, look at the relationship, and then can I say to them, hey, graph a function for that relationship. If it's 1 pack has 17 sticks, what is the function to graph that relationship? Is that y equals 17x, and we're graphing proportional relationships. Oh, I was supposed to do I have unique. Can you ask me like 2 more minutes? I gotta do one more thing. So sorry. And then could I also, thank you, whoa. Could I also, and now we get a non-proportional relationship. All right, so is everybody clear on that little bit? All right, so let's play I have unique. When I asked you to do 1700 minus 17, right? We had 100 packs. We got rid of 1 pack to get the 99 packs. That 1700 minus 17, let me go back here really fast. Those relationships, many of you, if you're like me and you were thinking about either the 1700 subtract 17, or then I think we got to 320 minus 3.2. To think about those, I need to own partners of 10, partners of 100, partners of 1,000, and when you get to decimals, I need to own partners of 1. So I encourage you to play a quick game with your students called I Have, You Need, where you literally say something like, you guys are adults, so I'm going to go straight to partners of 100. If I was a 1st or 2nd grade teacher, I would do partners of 10. So I'll say to kids, all right, partners of 100, if I have 70, everybody yelled out, you need 30. If I have 60, you need 4. Those are easy. Then I'll do the decades first. If I have 10, you need 90. But then I'll go to the 5s. So if I have 95, you need, okay, that was easy. But what if I have 15, you need, is that 85, 95, 75? Kids have to think about that a little bit. What if I have 35, you need 65, 75, but I thought 30 and 70, you work that out. Then you've done the 5s, then you do just numbers. So if I have 68, you need Ooh, that took a little bit longer for some of you. That takes a little bit longer for me. But you want to say to all of your kids from, boy, second grade up, they should know partners of 100. Third grade up, they should know partners of 1,000. Fourth grade up, they should know partners of 1. Partners of 1, so I say if I have 0.32, you need 0.68 to get to a 1. So I need to be able to also do partners of 1,000. So I need to be able to say I have 650, you need 350. Or I have 653. You need to be able to say that partner. If you can get those down, that is a routine that every teacher across the United States should be doing often. Oh, do that with yourself. Your drive home today, just start saying numbers and find the partner of 100 or find the partner of 1,000. Get to where you can do those like this, because that will build your numeracy in a huge way. Those show up everywhere. Partners of 10, 100, and 1,000. Okay. Building proportional reasoning, we just did it with unit ratios. One bag had 17 Skittles. One bottle had 3.2 ounces. So then I moved to problems like this, where I say, what if I had, come on, go away. What if I had slices of pizza, thank you, and they cost money? So what if I told you that I think it's 4, yeah. Oh, come on, stylus stick. My stylus isn't stick. Oh, it can't. One moment, please. Now I have to, I've been standing still too long. My bad knee is like not happy. Okay. Sorry, had knee surgery, it's all good. Almost better. Just on. Okay, I hate this stylus. I'm never using it again. Okay, maybe I won't use that part. All right, we'll just, here we go. What if I had 4 slices of pizza that cost $5? What if I had 8 slices of pizza? How much would they cost? I know that's really easy. With that, if I double the number of slices of pizza, do I double the cost? Yeah, so that's just 10. What if I had 2 slices of pizza? If I half the number of pieces, can I half the cost? Is that $2.50? What if I had 1 slice of pizza? Oh, I did that wrong. I wasn't looking at my card, so I guessed. You know what the next problem is? It isn't 1. My bad. Bad. It's 3. Because I don't want to suggest the 1 too early. I made it too easy for you. I want to ask you 3. Why? Because then I want you to have to find the 1 to get the 3. Yeah? So problem strings are in a certain order for a certain reason. And because I wasn't looking at my card, I went, right? So you'll notice that I have all of our strings written down. Problem strings are not where you just sort of make up problems. This one will work, that one will work. We think carefully about the relationships that we're trying to build, and so we have those problems in a certain order. We talk about them in between, share strategies, model them on the board before we do the next one. That's a problem string. I'm actually not going to spend too much time here. To get the 3, you have to find the 1, right? Well, you don't have to, but it's a nice way to do that. Can I get the 1 by either halving the 2 or dividing by 4? What is that? Is that 125? Then can I get the 3? And then can I get the 10? Can I place value up from 1 to 10? Ooh, and that place value shift is really important. I need to be able to think about 10 as times 1, and I need to be able to think about 1 as divided by 10. Anyway, so I want to do the same kind of problem strings. I would run the same sort of thing that I just did with the sticks of gum and the 3.2 ounces in a bottle with something like this ratio. I also like to do peanut butter chocolate chip cookies where you've got so much peanut butter for cups of chocolate chips. Take any of those relationships, those proportional relationships that you do, and you're going to end up solving a ton of proportions. Look how we just did it. This is not a whole string. I ran through the ran. Don't do that. Don't do it that way in your class when you're running out of time. This kind of problem string, you do those, you're going to solve 50 proportions in 1 5 to 10 minute with your class. Then you say, hey, you know how these are going to look? And then you say, all right, so it might look like this, that the ratio of 4 to 5 is equivalent to the ratio of 8 to 10. Or the ratio of 4 to that 8 is equivalent, right? This 4 to that 8 right there is equivalent to that 5 to that 10. And you're going to help them see that what they've been thinking and reasoning about, sorry about that, over here can be represented this way. So that when they run into a problem that's written as a proportion, like something crazy like, I don't know, 3.2 to 6 is equivalent to, I don't know what that is, to give me some random number, that they think to themselves, I can just put those in a ratio table and think up. I can just multiply up until I get from 6 to 15, and whatever I did, I'll end up with it on top of my ratio table, and I've solved a proportion. And they're using the exact same strategies that they've been doing: multiplication of whole numbers, multiplication of decimals, and division of whole numbers, and division of decimals to think and reason proportionally and solve proportions. And now they're not memorizing cross, multiply, and divide, but they're using dense connections to solve problems. I hope I've given you a vision of what I mean by what mathematics can be. I cross, multiply, and divide it. That's the only strategy I had for solving proportions. But now I am numerically powerful over proportions. I can think and reason proportionally. Okay, heading back here. I'm going to clean this up just a little bit.